labs? Stop it. Hurry. All right. So, guys, today what we're going to do is we are going to answer some unanswered questions. Along the way, we are going to learn two things. What happens when salt dissolves in water? They're called solutions. And then, guys, we're going to learn about something called colligative properties. Now, guys, I know that you're sick of hearing this, but you get to hear it again. In AP, we talk a lot about colligative properties. It's fascinating. There's so much rich stuff going on here. Guys, you're going to get a little taste of it today, but we don't do the deep dive on this until next year. But you do at least need to know the underlying principles behind it. So guys, today in class, what we're going to do, and don't write this down, guys, we are actually going to address two largely unanswered questions about what we've been doing over the last two labs. So guys, unanswered question number one is this. Why does water not boil at 100 degrees in Utah? But guys, let's establish the idea. Where does water boil at 100 degrees Celsius? Sea level. All right. Then guys, question number two is this. Why does adding salt to water make the boiling point go up? Now guys, understand, all of you have ideas about this. How do I know that? Because I listen to you read your conclusion answers to each other. You've all thought about this at some level. Guys, what we're going to do is we're going to figure out what's going on. So, guys, these are the two questions that we're going to talk about today. Along the way, we're going to highlight some things that are bigger ideas. But, guys, really our goal for today is simply to answer these two questions. So, guys, question number one is this. Why does water boil at 96 rather than 100? Now, guys, whether you write down the question or not is up to you. But, guys, this is worth writing down. In order to answer this question, and this is, guys, you're going to see this on the test. What are the factors that determine the temperature at which a liquid boils? What are the factors that determine the temperature at which a liquid boils? Now, guys, let's go in the Wayback Machine and let's talk about something we talked about. So, guys, this is alcohol. Specifically, this is methanol. Remember, we spilled it on the table and spread it out and it evaporated really quick. And then, guys, this is water. And, guys, as we were talking about this, we learned that ethanol boils at like 65 Celsius and water boils at like 100 Celsius. Talk to the person next to you about why. Why does water boil at 100 and methanol at 65? Chat about it. Let me interrupt for a minute. Just a moment. Guys, if you can't answer this question, there's a gap in your understanding that you need to address before the test. You should be using the word therefore, or at least the concept. Again, why does water boil at 100 and methanol at 65? Go. Got about 10 more seconds. So guys, I heard lots of great thoughts, but I actually was listening to Joseph, and I like your way better because I feel this necessity to use the word therefore, but I love that you just used so. It's such a better word. Lead us through it. Can you give us the so's? Okay. Yep. Yep. Okay. Mm-hmm. So which one has stronger IMFs? Water. So which one boils at a higher temperature? Water. See the so's? That was weird. But the idea is this, guys. Water's more polar. So it has stronger IMFs, so it boils at a higher temperature, right? So we knew that. Guys, one of the things that determines boiling point is the strength of the IMFs. Remember, stronger IMFs lead to higher boiling points. Because is there any, that's foundational, right? Anything there we need to explore? You okay? But guys, here's the thing. I asked you a couple minutes ago, where does water boil at 100 degrees Celsius? And all of you started babbling about sea level. Sorry, I tried to overdo that a little bit. Maybe it was offensive. Sea level is exactly the right answer. But guys, what I'm getting at is that has nothing to do with IMFs. So there's another factor that determines the temperature at which water boils, and it's atmospheric pressure. Charles, we're about to do your thing. So guys, what's the relationship? And let's just lay it out there and then let's talk about it. Higher altitudes result in lower atmospheric pressures, which causes the boiling point to go down. Guys, okay? Tell me when you're done writing this down, just stop taking notes for a long time. You guys okay? All right, you ready for a deep thought? I know it's early, but let's try a deep thought. So, guys, imagine if you can, and if you're really feeling brave, you can even crane your neck. Guys, imagine looking up and an opening in the roof were to appear and you could see outside the building. What are you looking at? You're looking first at the sky. And then amazingly, eventually, you're looking at the edge of the universe. And the Milky Way is sort of in the way. That's our galaxy. But guys, between us and the Milky Way galaxy and then the rest of the universe, which is made of an uncountable number of other galaxies, guys, we're looking at our atmosphere. Any of you know how thick it is? It depends on what you call the edge of the atmosphere. But guys, we typically say it's about 20 miles thick. There are weird ions between 20 and 100 miles away, but basically it's 20 miles thick. So guys, literally when you look up, there is a 20-mile tall column of air that you are looking through. Now guys, imagine this. You're at the Orem City Rec and you dive into the diving well of the swimming pool and then you look up. What are you looking through now? About 10 feet of water, right? But guys, here's the deal. That 10 feet of water you not only see, you feel. It's crushing your ears and it gives you a headache and it's sitting on top of you. You feel the pressure of that water, right? Well, guys, here's the deal. That air that is sitting on top of you right now is crushing you under tons of weight, of force. There's literally thousands and thousands of pounds of air crushing you right now. In the same way that if you dive to the bottom of a swimming pool, there's water crushing you. Guys, we are moving around in a sea of air, and that air is crushing you. So why don't you feel it? Guys, literally, why don't you feel it? Kind of built different, but that's not quite there.
Like compressing all around us instead of just...
No, that would be worse. It is compressing everywhere. It's pushing down and up and in. Guys, it's pushing from all directions. Why don't we feel it? Yeah.
Because air can compress water.
No. Guys, why don't we feel it? Because there's air inside of us as well. And guys, the air inside of us, we breathe, that oxygen flows throughout our bodies. Guys, the air is not only pushing in, it's also pushing out. And you've had this experience. So guys, the easiest way to feel this difference is you understand that you have what are called the station tubes. They're the little tubes that connect your ear to your nose. And guys, when you have a cold, that tube gets clogged. And so normally what happens is when like you go up into the mountains, there's less air pressure pushing on your eardrums, and your eardrums want to bulge out. But air comes down your station tube and it pushes out and it balances, and so your eardrums don't deform. But if you've got a cold, you've got air inside your eardrum and you've got air outside your eardrum. But if that eustachian tube is clogged, when you go up in the atmosphere, there's less air up on the top of temp. And now you've got this high pressure air inside your ear that's pushing out, and it hurts. But then what do your ears do? They pop. And that's literally what's happening, is that eustachian tube opens up just enough and it lets some of that high pressure air behind your eardrum leak into your nose, and it goes pop, and then the pressures change and they become the same and it doesn't hurt anymore. You guys not knowing any of this stuff? All right, let me show you an example. So guys, this is now your ear, kind of. But guys, this is the space behind your eardrum. And so guys, right now, this flask is being crushed by hundreds of pounds of air. Why is the flask not shattering? Because there's air inside it as well, right? But guys, let's do this. Let's get rid of the air. Okay, so now guys, let me get rid of all of the air by filling this completely with water. So now guys, how much air is inside the flask pushing back? None. So why doesn't the flask shatter? It's got water in it, number one, and that supports it, but also number two, the flask is pretty strong. But guys, there is no air inside that flask. So now what I'm going to do is I'm going to put a lid on the flask. Why does that lid stay on the flask? Because of gravity, but also because of air pressure. Guys, if you do the math, there's about 40 pounds of air sitting on top of this card. I need to switch cards because this just got wet. But guys, check this out. Those 40 pounds of air push in all directions, and it's enough pressure to support the water. So guys, the air pressure, this is getting wet and it's about to fail. The air pressure is pushing up, and that air pressure pushing up is supporting the water. Guys, this would not work. Well, here. Guys, this would not work if I did this, because now we not only have air pressure pushing down, we also have air pressure inside the thing pushing up. And now, oh, it did work. That wasn't enough. Oh, you know why? It's actually, adhesion. Guys, now it still worked. That is a pant low. So guys, this much gone air pressure. Okay, so now the question is, how much is enough? I've never done this before. So what about that? Is that enough? Wow, we're really close. But guys, that much missing air pressure is still enough. This is cool. I had no idea. Let's try again. I think if we do this, it's going to be oh, there we go. But guys, that much missing air pressure was enough to support the card. That's really cool. I had no idea it was going to do that. So guys, does this mental picture now make sense? The idea is this. When water boils, we already know this. If we have a beaker of water, in order for that water to boil, guys, it's got to break the intermolecular forces, right? But now you know that there's also air pressure pushing down on this, and it's got to overcome the air pressure in order to boil as well. So guys, at sea level, that's San Diego now. Guys, at sea level, there's about, there's 1,300 pounds of pressure on a sheet of paper. Guys, there's about 90 pounds of air sitting on that beaker at sea level. And guys, at sea level, for water to boil, it not only has to break the IMFs, it has to push back against those 90 pounds of air. Well, guys, now let's move this to Orem. So now, guys, if at sea level, there's 20 miles of air on top of this, in Orem, how many miles of air is on top of the water? About 19. We're at about 5,000 feet, 4,600, but it's close. So guys, we're about a mile up in the air. Guys, that means that there is in Utah a mile of air underneath us, and now only 19 miles of air above us. There's less pressure on the water, and so it boils at a lower temperature. Does that make sense conceptually? But there you go. So guys, what if we keep going? 20, 28. What's the height of Everest? 28,000 feet? Is it? Yeah, it is 29. So guys, Everest is about 29,000 feet, 5.5 to 6 miles. So now guys, at the top of Everest, you've only got about 15 miles of air above you. Guys, water boils in Utah at 96. On Everest, it boils at 68. But guys, what if you keep going? What if you go all the way to the edge? Yeah.
Why is snow able to stay on top? If it boils easier, does that mean there's more energy?
Brilliant. Chris, so many good questions there.
It's not the top of the mountain, but it's
Yeah. So talk about more energy. First of all, why are you thinking more energy? Yes. Takes less energy. Keep going. Yep.
Does that mean water also freezes out of the different temperature?
It doesn't. The freezing point does not change with air pressure.
So does it melt easier?
Also, no. It melts and freezes at the same temperature. But here's an interesting thing there's something really cool going on here. It turns out, and this actually even happens in Utah. Some of you are skiers, right? Have you seen, they call it hoar frost? If you've ever been up skiing on a day where we've had these amazing storm cycles come through, but guys, then the storms finally stop and you can still find these little stashes of powder, but the difference is that the snow no longer looks like it looked like when it fell, and it's all crystalline, and some people call it sugar snow. Actually, the technical term for it is surface hoar, and what is actually happening is it is so cold and it is so dry up at these elevations that when the wind blows across the snow, it actually causes the snow to go straight from the solid into a gas. It sublimates. And when that happens, what happens is the snow crystals, they don't melt, they get ripped apart. And as they get ripped apart and they turn into a gas, what's left behind are all these really freaky snow crystals that we call sugar snow, technically surface hoar, but that's what's going on. So at those elevations, it's not that there's more energy, it's just easier for them to go through these changes. Isn't that crazy? But it doesn't melt. Although, did any of you follow Utah Avi? None of you guys backcountry ski? I thought some of you did. Yeah, so they actually did a really interesting video. I was going to show Bittner today on what's going on in our snowpack, because actually what's going on is it's so sunny that the sun is hitting the surface of the snow and it's penetrating about 2 inches, and then it's melting the snow underneath. So you've got the surface hoar on top, and then you've got melting snow a couple inches underneath that. And at night what happens is it freezes and it turns into a crust. And then it's covered with this sugar snow. And if more snow falls on top of that, our avalanche cycle is going to go through the roof, because you've got a hard frozen surface with sugar and then more snow. It's going to be a mess. So anyway, there's so much cool stuff about snow science. So do you guys understand these ideas? Are y'all good? Please.
So how are the scientific term for it? When you have the right temperature and heat, where it's all 3 phases of that?
Yeah, it's called the triple point. Yep. Yeah, so it happens because freezing and melting and sublimation and those things are all dependent on temperature and pressure. And there's one magic pressure temperature combination where substances exist in all 3 phases at the same time. For water, it's actually about 1,000th of a degree above 0 degrees Celsius, and in an environment that is almost a perfect vacuum. It's about 2% away from a perfect vacuum. So if you can take water and if you can cool it down just to right above freezing, which isn't hard to do, but then if you can draw enough of a vacuum on it that it's almost a perfect vacuum, it's solid, liquid, and gas all at the same time. Kind of cool.
So why does it change, or why are they all the same?
Yeah, why does it happen? Yeah, and it's because the environment allows it to happen. I know, right? Are you coming back for AP next year? No, you're going to do you should go do physics. But if you want to sit down and talk about it more, we can. Guys, we can skip this. If you're starting to feel like, okay, I'm just kind of done right now, it's Friday and my brain's getting soft, guys, we can move forward. But what I would like, if you want me to, and it's totally up to you, guys, what I was planning on doing, but you guys always ask really good questions, and so our time goes long. Guys, what I wanted to do was show you what happens if we take this to the extreme. We understand that the boiling point is really low. What did we say, Joseph? 29,000 feet? At the top of Everest. What if we keep going? What happens to the boiling point? It goes down even more, right? What if we take it into outer space? Do you want me to show you, or should we just skip it and go on? Can I show you? Okay. Guys, this will take just a second to set up, but here's the idea. I want to sit down because this is hard to do, but I don't want to sit in that puddle. So let me clean up my mess really quick. So Chris, were you going to say something?
So I'm looking at too, as you go up and it gets the boils at 50 degrees Celsius. Is that triple point you're talking about?
Sort of. So water boils at, So 30, the number 32 jumps out in my mind because that's the temperature at which water freezes in Fahrenheit.
I meant like 0 if you get to.
Okay, so if you get to 0, you know water freezes.
Yeah.
But if you get to 0, just a skosh above it, in an environment that is almost a perfect vacuum, then it actually freezes, melts, boils, condenses, all of those at the same. That's the triple point. Yeah. All right. So guys, you ready? Check this out. How much air is inside this syringe? None. So there's no air pressure. But there's air pressure around it, right? When I pull down, how much air? Now there's air pressure inside the syringe as well, right? We're good on that? Okay. So guys, what I'm going to do, I got to get all the air out. Okay. So now all the air is out. So guys, why is this water not boiling? What are the 2 things keeping it together? Air pressure through the schnozzle, right? Air pressure, and what else? IMFs. So guys, you can clearly see that here. This water is not boiling because the IMFs are holding it together, and there's air pressure pushing on it. Now guys, what I'm going to do is I'm going to cover this with my thumb. and I'm going to pull down. Now, guys, imagine that my thumb was on this and I was pulling down. And when I pull down now, if my thumb is on here, what's going to be up here? Nothing. Air pressure is gone. What's the only thing holding the water together? Intermolecular forces. What will the water do? Now, guys, watch. In order to do this, and I promise you I'm not faking. If you want to try this at the end of class, you're welcome to. Remember our little game that we played with this? So guys, the idea is, why did this stick? Because there's air pressure pushing up. Guys, when I pull this down, it's super easy, right? Because I'm pulling down, but there's air pressure pushing down too. Guys, when I put my thumb over this, there will no longer be air pressure pushing down, and I'm going to be pulling down against the same force that held this in place. It's not easy. I think it's like 25 pounds. All right. The thing that really stinks about this is the air pressure is also going to ram my thumb down onto this little pointy thing. It hurts. Here we go. All right, so guys, watch the water. I'm going to pull it down here. Now my thumb is tight. The problem is I have to pull straight down, because if I pull it at an angle, it'll leak. Okay, let's try this. I hate this. Okay. No, I don't have a good enough grip. Just a second. All right. Oh, shoot. Okay, there we go. Guys, what's the water doing? Can you see it boil just like in your beaker yesterday? But guys, it's not hot. Okay, I'm done. Yeah, well, sort of, but think about it in the negative. Guys, what is it that keeps water from boiling? IMFs and air pressure. But if we can get rid of the air pressure, the only thing that's left is IMFs, right? And guys, the IMFs... Guys, the IMFs are not strong enough to hold the water together, even at room temperature, and you can see it boil, right? So guys, if you take water into outer space in a vacuum, it boils, because the IMFs, even at room temperature, are not enough to keep them from boiling. Understand, space is also cold, so it may not be warm enough, but guys, at room temperature, the IMFs are not strong enough to keep the water together. It's also the air pressure that makes the difference. Do you guys get the idea? All right, so guys, was that worth the 3 minutes? All right. So guys, let's keep going then. This then leads us to a question that you need to know the answers to. Guys, what can we do to make the boiling point of water go up? Well, guys, we know one of the answers is muck around with atmospheric pressure. Guys, this is stuff that's on the test. It's worth including in your notes. Maybe you already know it and then you don't need to, but... So guys, how do we increase the atmospheric pressure? Well, let's go back to our beaker. Oh, look, our beaker is in Orem. It only has 19 miles of air on top of it. Let's send it to San Diego. Now it has 20 pounds of air on top of it. The atmospheric pressure went up and it boils at a higher temperature. Decrease elevation. That's one way to do it. Guys, the other one sounds stupid until you find out it's smart. The other way to increase atmospheric pressure is to increase atmospheric pressure. You guys know in the dictionary under redundant, it says see redundant? Come on. I've got 3 chemistry jokes and 1 English joke. That's all I got. But guys, seriously, how do we do this? How do we increase atmospheric pressure? Which brings us back to an interesting question. People climb Mount Everest all the time. And those people need food. And that food has got to be light and portable, which means they carry dry food and then they cook it on the mountain. The problem is that water boils at such a low temperature up in the Himalayan peaks that the water does not get hot enough to cook spaghetti or cook rice. So how do they get around the problem?
I kind of like my question earlier, it's a bit dumb because
Yeah.
just assuming
It's not dumb, but keep going. What?
heat was involved, like weight, even though
Yeah.
that's not the case.
It-
That's,
It's the thing that causes it, but not the thing that determines when it happens, right? So guys, what do the mountaineers do in order to cook their food way up high? No, guys, it's and this is obviously not exactly the way they do it, but this is what you're going to be familiar with. An Instapot. So guys, how does an Instapot work? For those of you that don't know, guys, an Instapot is basically a beaker full of water, but you don't fill it. You just put water in the bottom so your food doesn't become waterlogged. And then what you do is you heat up the water and the water boils. The tricky bit is you screw an airtight lid to the top of this thing. And unlike your beaker of boiling water over the last couple labs where the steam goes away, where does the steam go? Nowhere. And guys, these molecules of steam up inside the Instapot are doing this. And they're running into the walls, and they're running into each other, and they're running into the lid. But guys, now that they can't leave, they're also running into the surface of the water at the bottom of the Instapot, and they push down. And when they do, the pressure goes up. And when the pressure goes up, it's harder to boil, and the temperature goes up. And so guys, in an Instapot, the water boils at about 110 Celsius. That's hotter, so it cooks your food in an instant. So guys, how do they do this in the mountains? All they do is the pans that they take with them to cook have a screwed on lid. But then guys, the question is this: why don't they blow up? No, actually, and this is really sad. Guys, this was some time ago. Do you remember, when those guys blew up those bombs at the Boston Marathon? Do you guys remember that? You know that they made their bombs out of Instapots? I don't know if you knew that or not. They actually took Instapots and they filled them with gunpowder, and then, because they're especially evil, they then put nails and bolts and screws inside of there so that when it blew up, it hurt people more. But they used Instapots because Instapot is a sealed container that eventually will fail. But guys, have you guys never used an Instapot before? You have. So Piper, you've seen this. It's this part back here. It talks to you. Guys, every couple minutes it goes psst, psst, and it lets some of the pressure out. Literally, guys, there's a weight that sits on top of a small hole. And as the pressure builds, eventually the pressure is enough to lift the weight, and it actually goes psst, and it allows a little bit of the pressure out. Now, if you have your grandparents' old school pressure cookers, they actually came with a set of weights. And you could put different weights on there, and that would actually dial in the specific boiling point that you want for whatever you're cooking. But guys, they have to leak or these things go not nuclear, but they blow up. So that's bad. All right. So guys, you good on that idea? You're learning so much today. Are you guys good? All right. So gang, let's wrap up the day. What about the other direction? Well, guys, we can also make the boiling point of water go up. We can also make the boiling point of water go up by making the IMF stronger. Guys, what did you learn in the last lab? How do we make the IMF stronger? Add salt. But guys, generically, the answer is create a solution. Add salt to water, add sugar to water. Doesn't matter. If it dissolves, the boiling point goes up. Guys, stop taking notes. There's one more thing you're going to write down. but it's going to be in about 7 minutes. Guys, in order for you to understand this, what I want to do is I want to share some videos with you. The first one is an animation. That means it's a cartoon. The second two are simulations. That means they're done on supercomputers and it's what it really looks like. But guys, in the last lab, when you dump salt in water, what was going on? Well, guys, first of all, let me show it to you as a cartoon. So guys, there's your salt. And guys, the water molecules, when you put salt in water, these water molecules come along like little tugboats, and they literally throw a rope to these ions. Those ropes are intermolecular forces, but they literally throw a rope to these ions and they drag them away in solution. It looks like this. Guys, this is what happens when stuff dissolves in water. The water molecules, through intermolecular forces, latch onto the thing and drag them into the solution. But guys, notice the way these are oriented. Dipole, dipole, dipole. Notice these are the positive ends of the dipoles. That's the negative guy. Notice dipole, you get the idea. Guys, this is the negative end of the dipole and this is the positive guy. Guys, that's why stuff dissolves in water. By the way, guys, when you come back for AP next year, we actually keep a running tally throughout the year. We are now on viewing number 13 of this video. We watched this video about 15 or 20 times during AP because there's so much going on here. But anyway, so guys, that's what happens when this dissolves. IMFs, and guys, you understand this, right? There are IMFs right here that cause these to dissolve. We should talk about this now. Guys, how do we know for sure that these IMFs between the water and the salt are really strong? How do we know they're strong? Because if they weren't, it wouldn't dissolve. Let that sink in. Guys, if something dissolves in water, we know that the IMFs between water and that thing are strong, because if they weren't, it wouldn't dissolve. Yo, let's keep going. So guys, let's do this then. That's an animation, that's a video, that's a cartoon. What does it look like for real? Guys, it looks like this. Slowed down about 10,000 times. Here's your water molecules. They grab a hold of the ions. It's not easy. But finally they pick them apart and the water molecules rip the salt apart and it dissolves. So guys, what does it look like then once the salt is dissolved? Guys, it looks like this. This is the mosh pit of the water with the salt ions trapped inside, getting the bajinkers beat out of them. Sometimes they touch, but they can't stay because they're being beaten up. And guys, this is literally what it looks like inside of salt water.
When all the water boils, start the
Yeah.
electrons and
Yeah, good. So when all the water boils away, the water's not keeping the NAs and CLs apart from each other and they recrystallize, just like in the salt and sand lab. So guys, let me do this. Ready? Stop. And maybe a little more. Nope. Go back a little. All right, so guys, what's the big idea here? Well, guys, the big idea is this. This is now a beaker of water. And this is the surface of the water where the water wants to boil. And guys, imagine that you are this water molecule right here. And you're like, I'm out of here. I'm going to boil. I got enough energy. Try to stop me. Well, guys, normally the thing that keeps this from boiling is the IMFs between the water and each other. But now, guys, we've got this intermolecular force to deal with. And what do you know about the strength of that force? It's really strong. How do we know it's really strong? Because it dissolves. And guys, that force is so stinking strong that water molecule is going, man, I'd really like to leave. And that ion's going, no, you're sticking around, buddy. I got you. You're not going anywhere. And so now it takes more energy to let the water go away and the boiling point goes up. You get it? Yeah. Oh, are you? Your hypothesis, but guys, do you understand the theory? You okay? You've got one more thing to write down and we're done. So guys, jump with me to here. Scratch down this one word. Then we're going to flesh it out and then we're done. Guys, the word is colligative property. A colligative property is a property of a solution. I should read it. I was going to paraphrase. A property of a solution determined by how much and not what type of solute particle is in solution. Remember, the solute is the salt. The solute is the sugar. The salt water is the solution. Oh, sorry. I'll just sit down. How about that? This is my favorite thing. When my classes are small enough that I can have this table all to myself. I have a place to sit. So Anna, we decided that you're going to teach the rest of the class and I'm going to just sit here. Here's the pen. You think we're kidding? All right. You. It's part of your punishment for being late. Yeah. It's actually being a teacher could be a punishment, and so consequently, yeah. Have you ever seen Hook?
Yes.
The movie, Robin Williams is sort of a take on Peter Pan, and Robin Williams. They're all sitting, the Lost Boys. They're all sitting at the table, and they're all being kids, and they're fighting, and they're like throwing insults at each other. Do you remember the insult that ended the whole thing? Robin Williams calls the kid a substitute chemistry teacher, and that's it. They had nothing with that one, and that was it. The game was over. Watch the movie. I was very offended. All right, so, guys, here's the idea. Colligative properties are properties that only depend on amount. Guys, could you really quickly in your brains remember the graphs that you drew for the last lab? Here's what happened. We add a little bit of salt to water, the boiling point goes up. What happens when we add more salt to water? Goes up more. What happens when you add more salt to water? Get the idea, right? That's a colligative property. So guys, why does this work? Talk to the person next to you, given what you now understand. Why does adding salt to water make the boiling point go up? Chat about it. That's next. Charles, you should be teaching the class. All right, guys, do you buy this? When you put salt in water, the IMFs get stronger. How do we know? Because if they didn't, it wouldn't dissolve. So when we add salt to water, the IMFs get stronger. Therefore, they're harder to break. Therefore, the boiling point goes up. This is what it looks like in too many words. If the solute dissolves, the IMFs are stronger. Therefore, the attractions are harder to break. Therefore, the boiling point goes up. Good? Do you need to write it down because you understand it? Okay. But guys, that's not the end of the story. Not only does adding salt to water make the boiling point go up, it also makes the freezing point go down. Guys, watch. You guys know that if you're ever buying a used car, you do not want to buy a used car that comes from Utah. California, yes. Montana, yes. Wyoming, yeah. Arizona, yes. Why not Utah? Because we salt our roads and it causes our cars to rust. Guys, in Utah or in Montana and Wyoming, they don't salt the roads because they figure people know how to drive in the snow. They do put down sand just to give us a fighting chance, but they don't salt the roads. So, guys, the question is, why does this work? So, check this out. This is the ice that is sitting on the Provo Canyon Highway roads as you're headed up to Sundance. And to keep you from hurting yourself, we want to get rid of the ice. So what do? Well, we add salt. Why does salt melt the ice? So guys, remember, these water molecules are attracted to each other, right? But what about their attraction to salt? It's even more. And as we add the salt to the water, or the salt to the ice, the salt literally picks the salt, just like we saw in the video. It picks the salt or the ice apart, and it causes the ice to melt. Get it? But guys, we don't have to wait for the ice to freeze, the water to freeze, for this to work. So they'll still go out on a warmer day like now, and the roads will be melted. But they still add salt. So guys, when it gets cold then tonight, chances are good the water won't freeze. Why not? Well guys, in order for water to freeze, it has to turn into this. But guys, did you know that when salt water freezes, the salt does not get trapped in the ice? Guys, try this. Go home, get a paper cup. It's easier to do in a paper cup. Put water in the paper cup, add a little bit of salt and stir it. Take a taste. Tastes like salt water, right? Now put it in the freezer. Let it freeze overnight, then peel the paper off and lick the ice. It will not be salty. Just a second. So guys, what's going on? And the answer is this. In order for water to freeze, it has to be able to create this structure. The problem is if these water molecules are attracted to salt ions, they can't form structure because they're tied up with the salt. So guys, what has to happen is these molecules have got to slow down more so they can finally break this interaction and turn into the crystal. Because guys, when water freezes, it leaves the salt behind. So the freezing point goes down. So now guys, think about what I told you about freezing a cup of ice water or salt water. So guys, this is what happens. As the ice forms, the ice crystals, I can't fit this in here, but the ice crystals form at the top. Where does the salt go? It goes lower. It stays dissolved in the unfrozen water. What eventually happens? Well, guys, eventually what happens is all of the salt ends up down at the very bottom of the beaker, or the bottom of the cup, and the water that's down at the bottom becomes so salty that it can't freeze. So what it does is it turns into this weird form of ice that's like a popsicle. You understand that a popsicle is not actually frozen, right? Why doesn't it freeze? It's because all of the sugars that are in the popsicle juice will keep it from freezing. You know that crunching down on a popsicle is different from crunching down on an ice cube. Guys, popsicles are not really frozen. That's what you're going to end up with here. You're going to end up with ice that doesn't taste like salt, and then you're going to end up with something that looks like popsicle guts, but it's actually the salt not frozen, but as close as it can get in the water. You get the idea? What's that? I mean, it's salt. It won't kill you. It'll make you thirsty. I mean, but try it. Lick it. See what happens. Yeah.
Rust undergoes similar things.
No, different. Yeah, that's a chemical and not a physical change. It's a different deal. So, guys, you get the idea? Chris, you were going to say something. Okay, so here's the thing that's really cool. Ocean water is salty, right? Yeah, and our blood is also salty, right? When we deplete the salts in our blood, we cramp up, right? We need electrolytes. It turns out that our blood is equally salty with salt water. So I don't know if you've ever done this, but I didn't try it out. It just happened. I was down in Cabo a couple of years ago, and I had kicked like a bench or something like that, and I had a cut on my leg, and I jumped into the water down in Cabo. It doesn't sting. Yeah, because the salt water, it has the same, it's called isotonic. It has the same salinity as your blood. It doesn't sting.
But if we take ocean water, we freeze it, and then we melt it,
Yeah.
and drink it.
Oh yeah. So think about this. So icebergs, right? Icebergs are frozen water, but there's no salt in there. So there are actually people that are talking about creating companies that go up to the North Pole, cut icebergs off the ice sheet, drag them with tugboats down to like New York City and melt them for fresh water.
And isn't it like also in like the Arctic or whatever, there's like different layers where the water's fresh water and salt water?
Yeah, because they have different densities. And water's weird. Any other substance, if you squeeze it, it tends to freeze. Water, it tends to melt. So that's how ice skates work. When you're skating across a sheet of ice, you're pushing on the ice and it actually causes it to melt. So you're actually sliding on a thin sheet of water. And so so up at those really crazy temperatures, the water can get salty enough that it doesn't freeze, but its density is different and you end up with layers of different saltiness. Yeah.
So is the reason you slip on the ice because of the ice or because of a really thin layer?
That's a good question, and it's actually the ice. The surface of the ice tends to be very smooth. And think about concrete, right? Concrete's got all sorts of jaggies in it, and that gives you traction. The ice is so flat that you slip on. You'd have to stand for a really long time to get that ice to melt. The reason that it works with ice skates is because we're taking all of your weight and putting it in a very small area, so it works there. Guys, let me do this really quickly. Homework assignment number 5 is our homework for tonight. Guys, please do not write incomplete sentences. Jot down thoughts. Now we can keep going. Yeah. Yeah, it's even different than that. And so, if you've ever taken your car and waxed it, what happens is the wax causes the water to bead up and roll off. The reason is because wax is nonpolar. So if you were to put water on the paint of your car without the wax in between, it would spread out because paint is polar. But when you wax your car, you're now putting the water on top of the wax. And the wax doesn't attract the water because it's nonpolar, so cohesive forces take over and the water beads up and rolls off. The same thing is happening to your skis. When you wax your skis, you're creating a nonpolar surface on the bottom of your ski, which allows it to travel faster over the water, the snow, because it cuts down on the attraction between the two. Yeah, that's why the snow, like if you've ever skied on unwaxed skis and you pick up your ski and the bottom is just covered with snow, it's because they're intermolecular forces, they're sticking together. Yeah, it's weird. Anyway, guys, crazy stuff, right? Homework assignment number 5, remember the test is on Tuesday. And then Chris, we need to talk about your lab, right? Okay, let me guys finish record. Let me shut off the recording. Guys, thanks for a fun day. You guys are amazing. Thank you. Let me do this.